Hello friends, welcome to this YouTube channel. Today we are going to solve a couple of numerical problems on AC series parallel circuits. By solving these problems, we shall learn how to determine equivalent impedance of a series parallel circuit. We shall also learn how to calculate values of circuit components, currents flowing through different branches, value of applied voltage, etc. for series parallel circuits. Problem number 1. A 230 volt 1000 Hz voltage is applied to a resistor in series with a capacitor C equals to 0.05 microfarad. When C is shunted by a voltmeter of capacitance 0.06 microfarad, the reading is 100 volt. We have to determine the current when the voltmeter is disconnected. Let us designate the nodes as A, B and C. Now we shall write down the given data. Supply voltage V equals to 230 volts. Supply frequency F equals to 1000 Hz. Capacitance C equals to 0.05 microfarad. Capacitance of shunting voltmeter CV equals to 0.06 microfarad. Reading on the shunting voltmeter VAB equals to 100 volts. Let the series resistor be RAC. Case 1. When capacitor is shunted by the voltmeter, equivalent capacitance CEQ equals to C plus CV. Using values we get 0.05 plus 0.06 equals to 0.11 microfarad. So we can replace this series parallel circuit by a simple series RC circuit where capacitance CQ equals to 0.11 microfarad. Now we shall calculate capacitive reactance. XCEQ equals to 1 upon 2 pi F CEQ. Using values we get 1 upon 2 pi into 1000 into 0.11 into 10 to the power minus 6, that gives us 1446.8631 ohm. Now we shall determine circuit current. I1 equals to VAB divided by XCEQ. Using values we get 100 divided by 1446.8631, that gives us 0.069115 ampere. Now we shall calculate equivalent impedance. ZEQ1 equals to V by I1. Using values we get 230 divided by 0.069115, that gives us 3327.7852 ohm. Circuit resistance will be RAC equals to root over ZEQ1 square minus XCEQ square. Using values we get root over 3327.7852 square minus 1446.8631 square, that gives us 2996.8 ohm. Given supply voltage V equals to 230 volts, supply frequency F equals to 1000 Hz. We have already determined series resistance RAC equals to 2996.8 ohm. Case 2. When the voltmeter is removed from the circuit, capacitance C equals to 0.05 microfarad. Now we shall compute capacitive reactance. Xc equals to 1 upon 2 pi Fc. Using values, we get 1 upon 2 pi into 1000 into 0.05 into 10 to the power minus 6. That gives us 3183.1 ohm. Now we shall determine equivalent impedance. ZEQ2 equals to root over RSC square plus XC square. Using values, we get root over 2996.8 square plus 3183.1 square, that is equal to 4371.8257 ohm. Let us now calculate circuit current. I2 equals to V by ZEQ2, that is equal to 230 divided by 4371.8257. That gives us 0.05261 ampere. Problem number 2. We have to determine the value of voltage to be applied at terminals AC in order that a current of 20 ampere may flow in the capacitor. Let us first jot down the given data. Capacitor current IC equals to 20 ampere. Let Z1 be 6 plus J8 ohm, that is equal to 10 ohm at an angle 53.1301 degree. Z2 equals to 8 plus J10 ohm, that is equal to 12.8062 ohm at an angle 51.3402 degree. Z3 equals to 5 minus J6 ohm, that is equal to 7.8102 ohm at an angle minus 50.1944 degree. Let us first determine Z2 plus Z3. Using values, we get 13 plus J4 ohm, that is equal to 13.6015 ohm at an angle 17.1027 degree. Now we shall determine equivalent impedance between terminals B and C. ZBC equals to Z2 into Z3 divided by Z2 plus Z3. Using values, we get 12.8062 at an angle 51.3402 degree into 7.8102 at an angle minus 50.1944 degree divided by 13.6015 at an angle 17.1027 degree. That gives us 7.3536 ohm at an angle minus 15.957 degree. In Cartesian form, this may be written as 7.0703 minus J 2.0216 ohm. Let us now calculate voltage drop across B and C terminals. VBC equals to IC times Z3. Taking capacitor current as reference, we get 20 at an angle 0 degree into 7.8102 at an angle minus 50.1944 degree. That gives us 156.205 volt at an angle minus 50.1944 degree. Now we shall determine circuit current. I equals to VBC divided by ZBC. Using values, we get 156.205 at an angle minus 50.1944 degree divided by 7.3536 at an angle minus 15.957 degree. That gives us 21.2419 ampere at an angle minus 34.2375 degree. We have determined equivalent impedance between terminals B and C. ZBC equals to 7.0703 minus J 2.0216 ohm. Impedance between terminals A and B, ZAB equals to Z1, that is equal to 6 plus J8 ohm. Now we shall calculate equivalent impedance between terminals A and C. ZAC equals to ZAB plus ZBC. Using values we get 13.0703 plus J 5.9784 ohm. This may be written in polar form as 14.3726 ohm at an angle 24.5795 degree. Now we can replace this series parallel circuit by a simple series RL circuit where R equals to 13.0703 ohm and inductive reactance XL equals to 5.9784 ohm. We have already calculated circuit current I equals to 21.2419 ampere at an angle minus 34.2375 degree. Now we shall determine applied voltage. V equals to I into ZAC. Using values we get 21.2419 at an angle minus 34.2375 degree into 14.3726 at an angle 24.5795 degree. That gives us 305.3027 volts at an angle minus 9.658 degree. Problem number 3. In a series parallel circuit, the two parallel branches A and B are in series with C. The impedance ZA equals to 10 plus J8 ohm, ZB equals to 9 minus J6 ohm, and ZC equals to 3 plus J2 ohm. And the voltage across C is 100 plus J0 volts. We have to determine the currents IA and IB and phase angle between them. Let us first jot down the given data. ZA equals to 10 plus J8 ohm, that is equal to 12.8062 ohm at an angle 38.6598 degree. ZB equals to 9 minus J6 ohm, that is equal to 10.8167 ohm at an angle minus 33.6901 degree. ZC equals to 3 plus J2 ohm, that is equal to 3.6056 ohm at an angle 33.6901 degree. Given voltage drop across ZC, VBC equals to 100 plus J0 volt, that is equal to 100 volt at an angle 0 degree. Let us first determine ZA plus ZB. Using values we get 19 plus J2 ohm, that is equal to 19.105 ohm at an angle 6.009 degree. Now we shall determine circuit current. I equals to VBC divided by ZC. Using values we get 100 at an angle 0 degree divided by 3.6056 at an angle 33.6901 degree. That gives us 27.735 ampere at an angle minus 33.6901 degree. Expression for current flowing through ZA IA equals to ZB divided by ZA plus ZB into I. Using values we get 10.8167 at an angle minus 33.6901 degree divided by 19.105 at an angle 6.009 degree into 27.735 at an angle minus 33.6901 degree. That gives us 15.7027 ampere at an angle minus 73.3891 degree. Expression for current flowing through ZB, IB equals to ZA divided by ZA plus ZB into I. Using values we get 12.8062 at an angle 38.6598 degree divided by 19.105 at an angle 6.009 degree into 27.735 at an angle minus 33.6901 degree. That gives us 18.591 ampere at an angle minus 1.0393 degree. Given voltage drop across ZC, VBC equals to 100 volt at an angle 0 degree. We have determined circuit current I equals to 27.735 ampere at an angle minus 33.6901 degree. Current flowing through ZA, IA equals to 15.7027 ampere at an angle minus 73.3891 degree. Current flowing through ZB, IB equals to 18.591 ampere at an angle minus 1.0393 degree. Now we shall plot the phasor diagram taking VBC as reference. IA lags the reference by an angle 73.3891 degree and IB lags the reference by an angle 1.0393 degree. By taking phasor sum of IA and IB, we get supply current I, which lags the reference by an angle 33.6901 degree. Now we shall determine phase angle between IA and IB. Phi equals to phi A minus phi B. Using values, we get 73.3891 degree minus 1.0393 degree. That gives us 72.3498 degree. Problem number 4. The circuit shown takes 12 ampere at a lagging power factor and dissipates 1.8 kilowatt when the voltmeter reading is 200 volts. We have to determine the values of R1, X1 and X2. Let us designate the nodes as A, B and C. Now we shall write down the given data. Supply voltage V equals to 200 volts. Supply current I equals to 12 ampere. Power dissipated in the circuit P equals to 1.8 kilowatt. Voltage drop between terminals B and C, VBC equals to 200 volts. Let Z1 be R1 minus JX1 and Z2 be R2 plus JX2, where R2 equals to 10 ohm. Now we shall determine impedance between terminals B and C. Z2 equals to VBC divided by I, that is equal to 200 divided by 12, that gives us 16.6667 ohm. Expression for reactance between terminals B and C x2 equals to root over z2 square minus r2 square. Using values we get root over 16.6667 square minus 10 square. That gives us 13.3333 ohm. Expression for impedance between terminals A and C, ZAC equals to V by I, that is equal to 200 divided by 12, that gives us 16.6667 ohm. Now we shall determine equivalent resistance between terminals A and C. RAC equals to P by I square. Using values we get 1.8 into 10 to the power 3 divided by 12 square, that gives us 12.5 ohm. Expression for equivalent reactance between terminals A and C, XAC equals to root over ZAC square minus RAC square. Using values we get root over 16.6667 square minus 12.5 square, that gives us 11.024 ohm. We have determined RAC equals to 12.5 ohm and XAC equals to 11.024 ohm. Given R2 equals to 10 ohm and we have determined X2 equals to 13.3333 ohm. Equivalent resistance between terminals A and B, RAB equals to RAC minus R2, that is equal to 12.5 minus 10, that gives us 2.5 ohm. Equivalent reactance between terminals A and B, XAB equals to XAC minus X2, that is equal to 11.024 minus 13.3333, that gives us minus 2.3094 ohm. Here negative sign indicates the equivalent reactance is capacitive in nature. Equivalent impedance between terminals A and B, ZAB equals to RAB plus JXAB, that is equal to 2.5 minus J 2.3094 ohm. This may be written as 3.4034 ohm at an angle minus 42.7301 degree. Equivalent admittance between terminals A and B, YAB equals to 1 upon ZAB, that is equal to 0.29382 mho at an angle 42.7301 degree, or this may be written as 0.2158 plus J 0.1994 mho. Again, YAB equals to GAB plus JBAB, or G1 plus JB1 plus BC. Capacitive susceptance of the lower branch between terminals A and B, BC equals to 1 upon XC, that is equal to 1 upon 20, that gives us 0.05 mho. Admittance of the upper capacitive branch between terminals A and B, Y1 equals to YAB minus JBC. Using values we get 0.2158 plus J 0.1494 mho, or 0.26248 mho at an angle 34.6864 degree. Now we shall determine impedance of the upper capacitive branch between terminals A and B. Z1 equals to 1 upon Y1, that is equal to 3.8099 ohm at an angle minus 34.6864 degree, or this may be written as 3.1328 minus J 2.1681 ohm. This is equal to R1 minus JX1. Therefore, R1 equals to 3.1328 ohm and X1 equals to 2.1681 ohm. So today we have solved a couple of numerical problems on AC series parallel circuits. By solving these problems, we have learned how to determine equivalent impedance of a series parallel circuit. We have also learned how to determine values of circuit components, currents flowing through different branches, value of applied voltage, etc. for series parallel circuits. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.